Okay, so we're going to kick off then with a black belt in spatial analytics. And for that, I'd like to help me welcome Stuart Lynn to the stage. Look at that.
No? Is that better? Perfect. Great way to start. So thank you for coming to the talk here today. Thank you for coming to the locations in general. I hope you're enjoying yourself. We've already heard a lot today about how analytics and spatial data can come together to give you amazing insights and really interesting insights into the world around us, into our businesses, into our nonprofits and our conservatory efforts. And today I wanted to get up here and talk a little bit about how we're trying to bring some of those techniques and ideas into CARTO, and how we're beginning to shift our focus away from visualization and exploratory analysis into more advanced analytics to help you understand your data better and do more with it. So I want to talk for a couple of seconds about what I would think of as traditional GIS. This is something that's been around for a long time. We all know it. We've all been in this field for some time. And traditionally, GIS, I think, has been a really powerful concept. It's done a lot. It's taken what was a very hard set of data to work with, which is geospatial data, made it very easy to manipulate and to visualize and to do some calculations with. And allows us to get a lot of insight into the world that we wouldn't normally have. And traditionally, GIS, I think, can be summarized by focusing on those three different areas. It focuses on organization of data, it focuses on visualization, and it focuses on calculation of that data. So if we think about that in the context of CARTO, what does that look like? Well, CARTO has always been a great place to organize your spatial data. For a long time, this is what people were predominantly using CARTO for. You would upload your spatial data to CARTO in the cloud, and then you would have a great PostGIS database waiting there for you to be able to organize, query, and ask questions of your data. We were also great at visualizing. So we could make really beautiful maps showing that data in a lot of different ways. We could do points, we could do polygons, we could do animated maps, we could bring to bear a huge cartographic language and a huge cartographic ability to really visualize that data in the way that it made the most sense and give you the most insight into that data, which is, again, a huge, hard thing to do. You've seen even more this morning, with CARTO VL, we're continuing that tradition to make these maps even more beautiful and even more interactive and even more understandable to people viewing them. And then through PostGIS, you heard Paul Ramsey talking earlier today, we were able to do a lot of calculations on those data as well. We were able to use this vast library of different methods to calculate really interesting things about your data. We have all these different functions that can do a lot of different things that can help you calculate interesting things about your data. And the way that I like to think about these operations is that they're kind of like the basic mathematical operations that we use with cartographic data. So if we think about numbers as being our typical way we think about data, for geospatial data, we can also think about it having operations that are like union, intersection, et cetera, to understand and keep calculations of that data. So then in summary, thinking about the kind of questions that we could ask using that stack, using that organization layer, the visualization layer, and the calculation layer, we can ask questions that are really focused on kind of like how and where questions. So if we think about it, when we're thinking about traditional GIS, the kind of questions we tend to ask are, how far away is something from something else? Can we calculate distances between things? How many things are in a given area? So if I have a polygon, and I have a number of points that are within that, how many of them are there, right? That's a simple, traditional GIS type calculation we want to do. We also want to do things like how big is a given area? What is the area of this polygon? How long is this line? How many, what is the area all these points cover? So again, a calculation that's about kind of how much quantities of things. Similarly, we could ask where are things? That's very much a visual question where we're putting things in the map. And then finally, the questions like, what is something closest to? And that's, I think, it's not unfair to say kind of what you could do with the original GIS stack. You could take that data, you could do those calculations, you could present it in different ways on maps, and you could use that to drive exploratory analysis and a visual-based analysis of your data. I think what's starting to happen now in our fields, and I think we heard it a lot today, is that we're moving away from kind of what I would think of as GIS, of geographic information systems, when we're interested in storing, organizing, and calculating with our data, to something that I think we can more properly term spatial analytics. So how do we bring kind of analytics to this field in a way that makes sense and we can ask more interesting questions and more complex questions of our data? So if the questions we can ask with GIS were the ones I mentioned before, I think in this new space, the kind of questions we want to be asking are, what is the likely cause of that pattern? Not just, how many stuff was over there, how much stuff was over there, but like, why is there more stuff over there than over here? Like, what is the cause of the pattern we see when we map this data on our maps using beautiful cartographic language? Things like, how much of an effect does one thing have on another? So often we're talking about cause and effect. We want to understand how, location drives sales, how location drives deforestation. How does one thing affect another? And again, that's something that is a slightly different question than we could ask using GIS. Other questions that can fit into the space are, like, where can I find where unusual things are happening? Where can I find outliers? Where can I find something that screams to be different from what I saw before? Again, this is something you may be able to do sort of visually, but it becomes quite hard when you've got very complex data. How would I organize things to be at a better reduced cost? What would happen if I tried to do something similar over here? What will happen when these locations tomorrow? So again, this is a set of questions that I don't think you can answer readily with the standard GIS stack, and we really need to bring to bear machine learning, statistics, and a number of other different disciplines to be able to understand that. And what I want to talk about today is some examples of that, how spatial plays into that, and how we are trying to enable those kind of analyses on the CARTO platform, how we're trying to bring these to the CARTO platform in a way that both data scientists, analysts, and business people can use them to make better decisions about their businesses, their nonprofits, their communities, et cetera. And another way to think about this is in a really very simple idea is that we can think about different types of analyses. And going from least difficult to most difficult, and providing least value to most value, we have kind of this path that is very familiar to anybody who works in sort of the analytics space. The simplest types of analytics we can do are the ones that I was kind of talking about before, the descriptive analytics, the how many, how far, where is it close to this thing. Those are analytics that are always what you start off with as a data scientist when you're trying to understand a problem. You want to really calculate as many numbers as you can, really describe the data that you have, really describe what it is you're seeing there. But it doesn't go that far. You can sort of produce that on a map, and it'll give you a snapshot of what you're seeing. It helps you break down things a little bit more, but it's kind of a little bit limited. The second thing we want to really do is diagnose things within that data set. So we want to say, well, okay, I can visualize these million points on the map, but what is that really telling me? Like, where are the interesting locations given all those points or all this data? If I'm looking at 20, 30 variables from the census and I want to see those in relationship to different neighborhoods, how can I begin to diagnose different patterns within that data set? How can I infer things about my data go beyond just creating summaries of it or viewing it on a map? Finally, we get into predictive, which is the one that everybody talks about all the time because it's the one that, if you get it right, you can make a lot of money. And we can really use predictive analysis to say, well, okay, I've got this pattern here. I kind of understand it. I've described it. I've looked at it, and I've kind of diagnosed a little bit of what was going on. Can I take that diagnosis and the description of the data, and can I make some kind of predictive model that will tell me if I look at another location or another time, what should I expect to see there? And so we've heard about that a couple of times today. We heard about it with real estate, for example, when people were interested in saying, okay, we can look at all this data for how houses have sold in New York over the years. Can I use that data to try and understand what houses are going to sell next year? So again, a predictive model to try and really see what's going to happen next or what's going to happen in a different location. And then prescriptive would be how do we actually make things happen? So everything we've been talking about up to now are analytics about reacting to data. We just got some data, we described it, we diagnosed it, we made a predictive model off of it. But what if I want to change something? What if I'm a person who's working in New York City Council and I want to dramatically reduce the number of bike deaths on the road? How do I know what policies to put in place to try and change the outcomes there? And that's a prescriptive analysis. So descriptive is easy. Diagnostic is fairly easy. Predictive is hard, and prescriptive is really hard. These are not easy things to do. And what we want to do is we want to build out a stack that allows us to go from one to the next and really increase in hard difficulty, but guide people through that process. And so what I want to talk about today are some ideas about how to do that. And I think in terms of that divide I was talking about before, traditional GIS really sort of only covers the first box there and maybe a little part of the second box. We can do, as I was saying before, these calculations, these visualizations, this descriptive analysis, and we can do a little bit of a diagnostic analysis, but without bringing in more complex statistical techniques or machine learning techniques. That's kind of where we really have to stop with traditional GIS. And what we're advocating for at CARTO is that really we want to be in the space of spatial analytics and to do all the rest of these different things. We believe in this so much that we ran last year the first Spatial Data Science Conference here in New York, where we invited over 130 participants to come in, well, 130 people to come and listen to things. We had about 30 people talking to talk about what we really think this landscape looks like, what a community in that landscape should be, and how we bring some of these interesting techniques to geospatial technology. And I think this can really be summed up by a couple of different quotes from an ex-astronomer, Clifford Stoll. And I like these quotes because I used to be an astronomer as well. But I think they really summarize what I'm trying to get to here. And he has this really interesting quote, which is, data is not information. Information is not knowledge. Knowledge is not understanding, and understanding is not wisdom. And I think that where we've kind of spent most of our time in the GIS realm for the long time is in the data and information section of this quote, and less so in the knowledge, understanding, and wisdom sections. And I think what we want to do is build tools that help us get to those extra statements. And just as a way of expanding on that a little bit, here's yet another quote, which is, data isn't information. Information, unlike data, is useful. So there's a first starting point where we have to change things. Well, there's a gulf between data and information. There's a wide ocean between information and knowledge. What turns the gears of our brains isn't information, but ideas, inventions, and inspiration. Knowledge, not information, implies understanding, and beyond knowledge is what we should be seeking, which is wisdom. So as professionals in this room who all work with data and all work with GIS and spatial data, really that's what we should be keeping in mind when we're thinking about data. We don't want to just be stopping at information. We want to be pushing through to wisdom. We want to be able to understand and act upon the data we really see in the world. And so I really want to go through 3 different examples of how this can play out. In my head, all data analysis can be broken down into either inference, prediction, or optimization. And so I want to give a couple of examples that we've worked on with the research team at CARTO and how we're bringing those into different projects and how you can think about bringing those into your own projects using CARTO as a platform. So with inference, what we're really trying to do is we're trying to infer patterns in our data. We're trying to say, given all this information that I have, what patterns are really there? And this is a fairly hard thing to do, especially within the modern world that we live in. You saw at Javi's talk this morning and a number of the other talks, the amount of spatial data that we're getting is overwhelming. We're seeing not just a huge amount of data, but a huge variety of data as well. And all that data makes it hard to find patterns and understand those patterns just by plotting things, just by making maps of things. And so with inference, what we're trying to do is really kind of sift out the information in that data. One of the most kind of common uses for CARTO for a long time was making really beautiful Twitter maps. So who here has made a Twitter map with CARTO? Yeah, about half the audience roughly. It's kind of one of those kind of nice gimmicky things that we had for a long time where you would put a phrase into Twitter and you'd hit go and it would grab all the tweets about that phrase. And then we could make a map showing all these pretty lights, showing all these tweets all across the country. And it told you absolutely nothing. It told you that Twitter was a thing and that people tweet things. That was more or less what you were seeing there. And the reason for that is because there was a lot of noise in that data. You can't just take those tweets and put them on a map and hope to understand something. We need to sort of really dig into that and infer patterns that are there. So what we really want to do is actually understand where are there clusters of tweets. And this map here you can see is a map that was made by the research team at CARTO that was looking at tweets about an earthquake. So with a lot of the fracking that's happening in Middle America, there's been a lot more earthquakes there. And in locations like Kansas, which never really saw earthquakes before, there's an increased number of earthquakes. So a couple of years ago, there was a report out that said, there's been this huge earthquake in Kansas. There was a lot of media coverage of it. And we kind of did what we normally did. We went to Twitter, we put in the word earthquake, and we hit get me some tweets, and we made a map of all the tweets. And again, it didn't really show anything. We could see, New York lighting up because people were talking about, earthquakes passively in New York, and there's just a lot more people there. We could see tweets in San Francisco because I think people talk about earthquakes all the time in San Francisco, regardless of what's happening in the rest of the world. But we could also see this little cluster in the center. And what we really wanted to ask was, could we infer the existence of this earthquake from the Twitter data? Could we actually dig out that signal from the Twitter data? And so we used a statistical technique known as Moran's eye to cluster the data into areas where there was outliers and areas where there was high clusters of data. What you can see here in the middle, the orange patch, is a highly statistically significant cluster of tweets mentioning the word earthquake. And the epicenter of that little cluster there is actually where the earthquake happened. So it is possible. We can take this noisy data from Twitter and we can infer something about the real world from it using statistical methods that have been around for a little while. You can do this in CARTO today. If you go into the analysis pane in CARTO, you can click on outliers and clusters, and you can create these statistically significant clusters of information that really help you pick out patterns that are there. We can do something similar with newer data sets as well. We don't have to think about just Twitter. We've heard a lot today about the new sort of information data sets that we're bringing onto CARTO in the next few months. So we have a lot of GPS data that is coming on from mobile phones that are showing human mobility. Very similarly, when we first started playing around with this data, our instinct was just to throw everything on a map. Just put 1 million points on a map and just see what patterns you could see. And it turns out, surprisingly enough, you can't really see patterns, right? It's really hard to actually detect patterns visually in that vast volume of data. So instead of doing that, we applied some clustering techniques to the data. So again, we're not using the raw data. We're inferring something about the data using statistics and machine learning to really pick out patterns. We did that in all the parks in New York. And from that, we were able to find regions in the parks where people tended to congregate together, spend a lot of time together. And it allowed us to make a map of shared experience in New York parks. We did this for large parks like Central Park, but we also did it for small parks like Maria Hernandez Park, which is near our office. And it allowed us to see how do people congregate in parks, where do they stick around for a long time, and how much time do they spend there with other people. And then that allowed us to ask the question, do large parks have more shared experience than small parks? And it turns out that they don't. So if you're really trying to optimize in New York for shared experience, shared community within parks, what you want to do is invest more in small parks rather than large parks like Central Park. So again, we go from this noisy data set that we could just maybe describe before or visualize before to something that can give us real understanding and real insight into the world and make our decisions based upon that data. We can do other fun things as well using clustering. So again, this is a data set that could have been fairly problematic, but using clustering, we can actually use it to sort of anonymize the data a little bit. So this was a study we did looking at the New York City Pride Parade. It was last year after some fairly unpleasant things had happened, and we wanted to really try and celebrate Pride in a meaningful way. And in New York, one of the things everybody's always thinking about is what bar should I go to? So we wanted to create a map showing kind of what is the bar exploration map of New York for after Pride. And so we went to one of the data sets we use a lot, which was talked about already, which is the New York City taxi data. And we looked at the path of the Pride Parade along New York. We looked at times just after the Pride Parade, and we looked at where people were being picked up and dropped off with taxis within that data set. Now, that's fairly sensitive information. It's fairly personal information. That's something that feels creepy to talk about, right? Everybody's feeling a little bit uneasy about that. If you're not, then you should be. That's just the way it should be. But using clustering, what we could take is all those drop-offs and pickups, and we could glob them together into areas that just had a lot of drop-offs. So instead of talking about one trip or one person anymore, we were talking about what were the mass patterns within the data. Again, not looking at individuals, but looking at where lots of people went to after the parades. And we found a whole bunch of different spatial clusters that corresponded to a number of bars, and that let us talk a little bit about what are people's typical trajectories after Pride Parade in New York going to bars. Again, from noisy data like the taxi data, we were able to infer something about how people move through the city after a major event, which can be something that can be used for prescriptive analysis for the city to understand what streets are best to close off, what streets are best to leave open, given this flow of people after the parade. So it's really interesting to sort of see how very simple methods can actually help us understand our data much better beyond just visualization. And finally, what happens if we have more than one piece of information about a place? As we increasingly, add more and more pieces of data to our collection of data, we're going to have these data sets where we have a location and we have about 100 numbers or 200 numbers describing that location. The census is a really good example of this. The census is this hugely complex beast where we have many, 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 many columns of information about a location. And finding patterns in that 100-dimension data set is really hard. So this is a demo that we just presented at Phos4G last week, which is actually using a machine learning method called TSNE to take all that data and to map it down onto a two-dimensional map. So on the right-hand side there, what you can see is a two-dimensional plot of all the different census tracts in New York, where all the census tracts that are close to each other in that two-dimensional plot are very similar. So as we move the mouse around that plot, we actually see different regions that are very similar to each other, that are maybe not geographically related to each other, but have the same kind of characteristics. And so again, one of the big challenges we're going to face as we move into the era of big data, of this like large, fast data, is that we're going to have these data sets where it's just impossible for us to visualize every single part of them individually by themselves. So again, by applying some machine learning, in this case, a dimensional reduction algorithm, we can start to map things out in terms of the relations and then explore and put on the map those like relations between different things. And it helps us, again, get much more insight. Little clusters in this plot on the right-hand side here could represent all the areas where you're seeing like large amounts of development or large different shifts in cultural and ethnic sort of boundaries in New York, or income or education, et cetera. And again, it's a way of visualizing and summarizing your data that's much more useful than just like putting it on a map in general. The second kind of big area where I think we can start to make some interesting strides with geospatial data and CARTO as well is optimization. So this comes up all over the place. We see so many of our customers saying, I have this large, complex supply chain. I have this large, complex problem that exists in the world. How do I like optimize that? If I was going to open a new store, where should I open that store to make sure that I'm getting the best costs, the best profit and the least costs? I have to, close one of my factories. Where should I close a factory to like minimize the impact on how much money I'm going to make and increase costs? And optimization is hard because if you think about it, let's think about like opening a store in New York. There are thousands of buildings in New York, all of which may have like some retail space available. If you're trying to understand where you want to put a new store, that's going to impact your supply chain. How do you get materials to that store? It's going to impact the kind of customers that are going to be present around that store. And there's a lot of variables to really take into account. If we're just using descriptive analysis and visualization, it becomes really hard to like try out all the different scenarios. You can see, okay, well, if I move here, show me a map that shows me what my costs are going to be and what my customers are going to be. If I move over here, do that. But then with 1,000 stores, you don't want to be iterating through every single one of those ideas. So with optimization, what we try and do is we use statistical techniques to really kind of find the best solution in that space. So one of the use cases that we've had for a while at CARTO is supply chain optimization, and I think this video is hopefully going to play. And what you can see here is the blue dots that are displayed here represent trash processing areas. So these are locations where people are bringing garbage from residential areas and industrial areas. And each one of those is a capacity. So each one of those has a certain amount of material it can process in a day. They also have a cost associated with processing each kilogram of the data. And then all the yellow points are locations where that trash is coming from. And so a common use case we find for geospatial analysis is what one of those centers should I be sending my trash to for each one of those locations to minimize the cost, the driving cost and the cost of processing the waste of the center, and make sure that none of those centers go overblown, and make sure that none of those centers actually get too much trash to be able to process them. And this is a classic optimization example that we've built into CARTO now is a sort of a tool set and an analysis where you're trying to say, I want to optimize my profit while minimizing my costs, but I have these constraints. I can't send this amount of trash to this station. And that turns out to be a problem that's like fairly well understood and fairly well solved. And what we're doing in CARTO is bringing in tools and analyses to be able to do that with lots of different problem sets. We're also building that into applications. So this is an application that was built by one of our partners that's looking at bringing together routing with that kind of optimization problem to say, again, for trash compaction, trash type project, if I know all the kind of places that are producing trash in my city, how should I send out a fleet of trash collection vans? I'm saying trash a lot. That's weird for me because I'm from Scotland originally. So I'm just going to say rubbish, if that's okay. Let's look like where do we go and pick up rubbish at different locations and in what order to kind of minimize our cost and to keep our drivers busy? And then again, beyond that, how do we maximize it so that we are using the fewest vans on the road at any given time to kind of reduce CO2 emissions? So these kind of analyses, again, go beyond just visualizing or summarizing data. They're about really digging into it to find the best possible solution. And we want to be bringing those types of analyses to CARTO and to the GIS world in general. And that brings me to the final section I wanted to cover, which is prediction, which again is like one of the hardest things to do, I think. We've heard a lot this morning about the real promise of AI and machine learning. We heard some of Google's slightly creepy phone calls to businesses and how that goes, which is interesting. But I personally think that the more mundane uses of AI and machine learning are way more interesting than the kind of very complex things that we see from Google and Facebook. I think there's a lot to be done just with simpler models, with simpler techniques that can really sort of drive value in data sets that are geospatial. And there's been a lack of use of these kind of methods within the geospatial industry. I think some of the talks we heard before this for real estate from Hodges Wog Elliott were starting to go down the right route of how do you bring these predictive models to geospatial data in a meaningful and interesting way. So I want to talk through a little bit in more detail how you might think about that. So let's really think about the problem. Our prediction problem is, given some existing data, can I predict some target value in a new area or at a future time? So what that's saying is that we have a lot of information about the world. We've collected through surveys, if it's something like the census, or we've collected through mobile phone applications, if it's like a GPS data set, or if it's like a retail case, we might have a lot of historical data from a company about the performance of their stores and what they're selling there. And what we're interested in doing is saying, can I predict that somewhere else or in the future what that value is going to be? So that might be the profit that a company makes, it might be the profit a given store makes, it might be the number of traffic accidents in a city, it could be anything, right? But what we want to do is we want to find a way to predict that at some future time. And this is hard, right? This is a hard thing to do with any certainty. Like prediction is a hard thing to do. So how would we maybe solve this problem? Well, I love this summary of how the machine learning crowd thinks to solve this problem. From XKCD, which is, you put the data in a big pile of linear algebra, and then you collect the answers on the other side. What if the answers are wrong? Well, we stir the pile, and then they start looking right. And that's, if you want a summary of how machine learning works, how machine learning works. We try to learn the patterns in the data by taking the data, and then automatically learning a model that describes that data. And that's basically all machine learning is. Whether you're answering phone calls through a Google engine, or if you're just trying to predict your store's profit, this is basically what's happening behind the scenes. So the first thing we need to do is really kind of create some features for that model to use to try and predict. So what we want to do is we want to think about things that may impact the thing that we care about. So let's say it's something like the number of car accidents in a city. Well, the different things that are going to affect that are weather, the number of cars that are in that area, sort of historical trends with car accidents within that area. You may think about how many bars are nearby. That may increase the chance of drink driving. You can look at road quality. There's all these different variables that come to play that might affect the number of deaths that you see on the roads within a city. A lot of those things are about the thing you're interested in itself. So, for example, let's think about whether we're looking at the success of a store or a cafe, for example. So things that may affect the success of a cafe are things like its square footage. Does it have free coffee? If you're a cafe, then it's probably not a great strategy to get a lot of people in. But you might want to see that you get a free coffee when you go in there, and that may affect the profit that location makes. But then other variables are going to be much more spatial in extent. So I think, again, what we heard from a couple of the other speakers is that it's not just the details about the location itself, it's about everything that's around it. So if you're a cafe, what are the businesses that are nearby? If you're downtown in the financial district in New York, then you're going to see a lot of success from people coming in during their lunch breaks, but maybe less so on the weekends. So the number of businesses and the types of businesses around you might affect how successful you are. How close is the nearest subway? What is the context of the data set itself? And thankfully, that's where geo comes into play really well. So we saw this slide in Javi's talk this morning. I really like this slide because it shows you kind of the wealth of information that is available to create these features when you think geospatially. These should all be animating. Unfortunately, just the top left-hand one is. This is the UK census, and this is every variable in the UK census being shown for like a split second. So if you think about it, all those pieces of information that we know about those locations in the UK can all be features that help us understand better our data and help us build these predictive models. And we have this for a lot of different countries. Oh, there we go, started playing. Just needed a little bit of time to wake up. So again, we have this for the UK census, we have it for the American census, Spanish census, and the Mexico census. But just to give you an idea of the wealth of information that is available for a given location, we have lots and lots of different things there. We also have newer data sets. We have data sets like Javi was talking about this morning, like foot traffic data. So how many people are going past an area at a given time? What kind of demographics of those people? Like how are they spending? How are they moving? And again, that can be a really powerful feature in some of these models. And so once we've collected all those kind of ideas together, data about the locations themselves, but then also about this universe of information we have because we know that event took place, we have to learn how those things relate to each other. And that's the stirring of the pile of geospatial data with machine learning. So what we want to do is we want to make this a kind of exploratory analysis. And so what I wanted to show here is a prototype application we'll be building out on the research team that really tries to understand how we may be able to make that process iterative. So the white dots you can see here are locations of fast food restaurants within Boston. They're sized by the amount of money that each one is making. And what we're looking at here is a couple of different variables associated with each. So we're looking at the store size, and we're looking at whether or not there was a given promotion on that store. And what we can see on the right are the kind of graphs that show how the store is doing versus those two variables. And so there's not much of a pattern there, and it's actually really hard to pick out what the pattern might be. So what we can do is we can try and train a model on that. And what you're seeing in the top right-hand side now is the kind of the prediction that we're making on the y-axis and the actual value of the stores on the x-axis. And you can see it's kind of just noise. This is kind of just a mess. So with just the information about the store itself, we can't do very well with predicting how well it's going to do. So instead, what we can do is we can appeal to some of this geospatial data that we can join with that. So if we look, say for example here, this is a layer showing the number of different businesses in different categories that are in Boston. We can use that data, so how many different restaurants were in this area, how many different real estate agencies, how many different dentists, et cetera, as features that may help us better understand whether a store is going to be successful or not. So what we can do now is we can rebuild that model using that business data, and we do a little bit better. So you can see here we can sort of skim through and see the different features that we have there, all the different business types. And if we can skip the video ahead a little bit, I don't have control up here, unfortunately. But we can see here the correlations between those different business types and whether the store is going to be successful or not. And so we can see that, for example, bars and nightclubs are kind of a good predictor just using a correlation. But again, we can train a model, and behind the scenes, this is using a technique known as gradient boosting. And then once that model is trained to predict these values, we see that we're going to get a much better result than what we had before. It's going to take a couple of seconds. But basically what we end up getting is a much better correlation there, right? So for our prediction and our actual value, we get this much tighter correlation. And we can keep continuing to do that. We can add in the foot traffic data from GPS. We can add in data from a number of different sources. And they keep helping our model get better and better at predicting the outcome. One of the nice things about this type of model as well is that it also gives us insight into what is driving the profit in our stores. So when we look at the different importances of how important each feature was to how well the model did, we can see that there's different features that kind of will give you more predictive power and less predictive power. In this case, again, bars and nightclubs is a huge predictive power for this fast food chain, which again, that's something you might use to decide where to place things. So again, with the foot traffic data, we can bring in now foot traffic over time. So look at how many people are in a given area in the morning, the evening, and the afternoon. You can see here a little animation of that, which is nice. But again, the real value in this data is not the animation or the visualization. It's using it as a component of this predictive model to help us understand how these stores are doing. So again, we can train the model using this data joined with the store data, and that ends up making our data even better. So I'm not going to let that play out here, but it gets a little bit better in the end. And we think this is a flow that we really want to push at CARTO, is using these kind of machine learning analytics along with these kind of iterative visualizations to make the models that you're producing better and better and better in a very tight time constraint. So here you can see we just add in more data, we train model, and we get the results, and you can see those really easily. In terms of what you can use today in CARTO, we're looking at a lot of the things that I talked about just now are already available on the platform. So for prediction, we have gradient boosting regressors, geographically weighted regression, and spatial Markov chains. Don't worry if you don't know what that means. They're just all different ways of doing prediction. We have the clustering type algorithms that I was talking about before available, all as functions on CARTO SQL. And we want to really kind of bring this to a larger audience. So right now, a lot of what I was talking about is available through the SQL interface in CARTO, or some of it's available through the kind of the analysis panes in CARTO, where you click through and can visually change things. But we want to make these kind of analyses available all the way from CARTO Frames, which some of you maybe heard about this morning, through to applications that people want to build, through to the builder and self-service tools. So over the next year, what we're going to be doing is working really hard to build a lot of these analytical solutions into the engine part of CARTO, so the central part of CARTO, so that data scientists can utilize them in CARTO Frames, location intelligence solutions can utilize them in location intelligence solutions like Traffico and the other ones we've been talking about. Decision makers can utilize them within the builder using a point and click interface, and developers can use them in whatever they want to use them in through an analysis API. One of the flows that we're really interested in is using CARTO Frames to prototype out analyses. So taking these building blocks that we're producing for inference, prediction, and optimization, composing them together in a very quick analysis framework like CARTO Frames, and then being able to deploy those on CARTO as full end-to-end analyses that can be used again and again and again in different applications. So we could prototype them there. We could access them in Builder using nodes, analysis nodes like you can see in the Builder currently. And then also bring them to play in location intelligence solutions when you guys need to build these for your clients to use day in and day out. And so we're really excited for that future. We're really excited to build out some of these more powerful analytical techniques in the platform. We'd love to hear from you about the challenges that you guys are facing and the kind of questions you're trying to answer, especially if you fall into those kind of where is, how is kind of categories. And if you've got any questions, I'd love to talk about them there.